So we're starting a new unit. The majority of this unit will be focused on the foundation of functions. We will intertwine things like sets of numbers, algebraic expressions, algebraic equations, and other things, but the majority of our focus will be on the foundation of functions. And there are some things from Algebra 1 that you need to remember. The first thing you need to remember is that the variable x had other names that it inferenced that we're discussing the variable x. First of all, it was called the independent variable. The other thing that went with that was the word domain, which we will be looking at a lot today. The other thing we used to refer to the x variable is input. For the y variable, it is the dependent variable, the range, and the input and the output. Sorry. So, if you look at a table and dependent, a lot of people remember these terms by using Dixie-Royd, which stands for domain, independent, the x variable and input, the range, the output, the y variable, which is dependent. Okay, independent and dependent reference the variable. Domain and range reference the set of values. Input and output reference the specific elements that we either input into the function or output out of the function. The other thing I want to really quickly remind you is that a function is a one-to-one. The definition of a function is for every input there exists only one unique output. That means if I input the number 1 into the x variable to find what the y will be in the table, I can only get one y. So go to the next page to see some examples of functions and non-functions. So for example, if I were to make this table, and 1 gives me a 5, 2 gives me a 7, 1 then gives me a -3. This cannot work because 1 cannot be matched to more than one number. If I were looking on a graph, and I were looking at a graph of a line, then this value of x right here goes to that point, which gives me that y output. This value of x right here goes to that y, giving me that y output. There's only one output for each input. But if I were to draw a graph like this, you can see that at this x, I have this point, but I also have this point. This would not be considered a function. It does not pass what we use, the vertical line test. If a vertical line hits twice, which is indication that the x value right here is used in two separate points, then this is not a function. And this should all be review. So let's go ahead with the Algebra 2 stuff. So you should have a copy of this worksheet in front of you. If you don't, I will make sure that it's in the Google Drive so you can download it and print it. But we're going to put this first graph on in black. And then we're going to go ahead and do this second in red. And we're going to fill in all of these characteristics down here. So this first graph I know is a line. And I can see that I can find the x-intercept very easily by plugging 0 in for y, I get 5. And by plugging 0 in for x, I get -3. And if I were to plot those, I would see that I would get a line. Now I'm going to look at the characteristics of this graph. The domain is the list of all real numbers that are used for the input value. So the domain is the list of all values used for the input. So really, when I refer to domain, I refer to left to right. So if I were to look at left, so my left of my graph is over here, but what does that arrow tell me? That arrow tells me that this graph is going to keep going left forever. This graph is going to keep going left forever. So this graph goes from -infinity to +infinity. Now, we have two other notations, and I'm going to write them in here. If I were going to use inequalities, I would say -infinity is less than x, which is less than infinity. Set notation I'll look at with range so I don't get too much junked in here. So range I refer to as bottom to top. So the range of a function is a list of all y values. So this is bottom to top. And in your notes, I probably would not write B to T. I would write bottom to top. So integral notation. Integral notation would be just what this obviously goes from bottom. This is going to keep going down, and this is going to keep going up. So I'm going from -infinity to +infinity. So integral notation would be -infinity to +infinity. Notice for a minute that I'm using parentheses here. That's going to change when I come over here to this graph. Okay, I want to teach you set notation. Set notation uses curly brackets, and it says y such that. And it would be, then I would put the inequality. -infinity is less than y, which is less than +infinity. Curly bracket. I really want you to try to keep your answers right in here in this column so that we can add answers over here. I can clear my column when we move over here to this graph because mine is smaller than yours, but you should be able to fit all of this down this column. Okay, so I'm going to move on to end behavior. End behavior is a statement where it says, as x approaches, that long arrow stands for approaches. So as x approaches +infinity, so as my x is getting bigger, the function of x is approaching what? Well, as x is going to +infinity, this function is going to +infinity as well. So f of x is approaching +infinity. We have two end behaviors because x can approach positive, but x can approach negative. So as x approaches -infinity, my function is also approaching -infinity. Where is it increasing? It is increasing from the bottom to the top. It is not decreasing at all. I have a y-intercept of 0, -3. Go ahead and write that in here, 0, -3. I have an x-intercept of 5, 0. I want to make sure that you understand that our x-intercept is also referred to a lot of times as the solution. So these two things, whoa, don't know what I just did. These two things, the x-intercept and solution, are the same things. So this guy has a solution at 5, 0. A maximum and a minimum is if my graph had a maximum value or if it had a minimum value. And this does not have a maximum value or a minimum value. So these graphs, they just keep on going. So they don't have a max and they don't have a min. So I expect you to have filled in these three right here. Okay, now let's move over to this other function. So I'm going to pause and erase. So now we're going to look at this side of the slide. We're going to look at this, which is known as a quadratic. Because it is a squared right up there, this is a quadratic function. And I don't know how much you remember quadratic functions, but I'm going to go ahead and just graph this for you and fill in the table. This is a quadratic function. It is a parabola. And again, I can tell it's a parabola because it's an x squared. Please pause right now and copy down the table and the graph. I am now going to do domain, and I'm going to do domain in set notation. So I'm going to be filling in this column right here. So remember, domain is how far left, what x values does this guy use? How far left will this go and how far right will this go? This is a continuous function that will keep going all the way right and all the way left. So set notation says x such that it goes from negative infinity to positive infinity. That is set notation. So now let's talk about range. Range goes from the bottom to the top. Now here's the thing, I have a bottom right here, right? I have a bottom of a graph. It doesn't go past that right there. What is the bottom of this graph? Well, we know that we plotted this point on the bottom, so the bottom is negative 12.25. And I actually have a point right there. So my range in integral notation is going to go from negative 12.25 all the way forever to infinity. So I'm going to write it like this. Negative 12.25 to infinity. Now, why do I have the hard bracket versus the soft bracket? The hard bracket is because I actually have a point there that I can touch. For any point that I don't touch, I can't touch infinity because as soon as I touch infinity, it moves. So that's why I have a soft bracket. How would that look in inequalities? So that would be range y is greater than or equal to negative 12.25. End behavior. As x approaches positive infinity, so as my x gets bigger, what's happening to my y value? As my x input increases, my y is also increasing. So my function of x is also increasing. Now here's something different than the line. As my x gets smaller, what happens to my y? Well, my y is also increasing. I always refer to y as the function of x. This is the function with x inputted into it. Okay, where is it increasing? Well, increasing means moving up. So this function is increasing from here up. It is decreasing on this, and it is increasing here. So it is increasing from this point up. So I know this point. We refer increasing. Where is it increasing? It's increasing from 2.25 all the way. Why do I get the 2.25? Because of my vertex right here. So I am increasing from this point all the way to that way. So I'm increasing from 2.5 to infinity. I'm decreasing from negative infinity to 2.5. So I'm decreasing on this guy. He's going down, he's going up. So I'm going downhill here, I'm going uphill here. Remember, positive slope, negative slope. So I'm decreasing on this function. I always go from the smallest number to the largest number. So smallest number to largest number. Does it have a y-intercept? It has a y-intercept. And my y-intercept is 0, negative 6. If you can write that in there, the y-intercept here is 0, negative 6. We can go ahead and add that, and I probably missed it. Should go through that point right there. Does it have an x-intercept? It actually has two x-intercepts, doesn't it? It has the x-intercept of negative 1, 0 and an x-intercept of 6, 0. And those are also called solutions, so if you can write that in here. Now we can talk about maximum and minimum. So maximum point is the highest point. Well, there is no maximum point here. Okay? This is just going to keep on going up, but we do have a minimum point here. And this is an absolute minimum. There is no point that's lower than that. So we call this point the minimum. So we are at 2.5, negative 12.25.